Alright, hey guys, today we're going to go over our waves and sound review with some fully worked out solutions. Let's get started with number 1. A rotating fan's blade spins with a frequency of 12 Hertz. Calculate the period of the spinning blade. Okay, so here, when we're dealing with frequency, a lot of people, they jump right up to this equation right here. They say frequency is 1 over time period. It's given, it's on our equations, let's use that one. Well, that is an equation that works for frequency, but it's not the equation you always want to use. This t right here, it's not just any time. That is very specifically the time period, or just the period of an object or of some cycle. The period is how long it takes to perform one full cycle. The frequency is the opposite of that. The frequency, and this is our definition of frequency really, is how many cycles occur in some unit of time. Really, that is cycles per second. So, if a rotating fan's blade spins with a frequency of 12 Hertz, calculate the period of the spinning blade. The period is going to be the inverse of that, where frequency is cycles per second. Time period is going to be the seconds per cycle. And these equations are really where you want to start with frequency and time period. But if you have one, because of our equation that we highlighted up here, frequency is 1 over time period, they are inverses of each other. If we look and we see, well, frequency, cycles per second, time period, seconds per cycle, all we've done is we've flipped the numerator and denominator. So that means if we have a frequency or a time period, we can get the other by just plugging it in to an inverse. Say we have the time period. Plug in the time period, 1 over the time period gives us frequency, 1 over frequency gives us the time period. So here, we're given a frequency, 12 Hertz. Let's find our time period by using our equation 1 over the frequency right here. Time period, 1 over frequency. Frequency is 12 Hertz. We get 1/12. What is our unit here? Well, our unit is going to be seconds. Alright, for number 2, if it takes the rotating fan 8 seconds to rotate back and forth, calculate the frequency of the fan's rotation. So here we're asked for a frequency. We know frequency is cycles over seconds. There is one full cycle, right? One rotating back and forth. That's a full cycle. Over 8 seconds. 1 over 8 is our answer. Now, of course, we could write this out as a decimal if we wanted. This could be 1 over 8 is 0.125 Hertz. Make sure to tack our units on there. If we're struggling with frequency and time period, the biggest help would be remembering that frequency has units of Hertz, time period has units of seconds. Using the units, you can always remember, oh, time period has seconds in the numerator, because whatever your unit is informs you of what order to put seconds and cycles. If your units for time period and units for time period are seconds, you're going to put seconds on top, cycles on the bottom. If your units are Hertz and frequency has units of Hertz, you're going to put seconds on the bottom. Use that to help you remember what is the equation for frequency, what is the equation for time period. Okay. Then, number 3, by shaking a slinky faster and with larger arm movements, do the speed of the waves created increase, decrease, or stay the same? Explain your answer. Well, if you remember us going through this in class out in the hallway, shaking a slinky, no matter how fast we moved the slinky back and forth, no matter how dramatic and large we made our arm movements, the speed of the waves stayed the same. Now, why is this? We're asked to explain our answer. Well, the speed of a wave is set by the medium. And in the case of making a wave on a slinky, it is the same slinky. Nothing about the slinky is changing when we increase our frequency or when we increase our amplitude. It's still the same slinky, so the speed of the wave traveling is gonna stay the same. Another example, if you're talking, right? Generating some sound waves, that sound is set to a certain speed by the medium. Oftentimes, when we're talking about speed, we get this equation. Velocity is frequency times wavelength, all the way in the top left, right up here. A lot of people want to jump right to the equations and say, oh, velocity is frequency times wavelength. Take the frequency, take the wavelength, you get the velocity. That's absolutely true, but velocity is not set by the wavelength and the frequency. The speed the wave travels is set by the medium. That medium determines how fast, how big this velocity is. And then based on this velocity, you get a range of wavelengths and frequencies that are possible for that given medium, for that given velocity of the wave. Number 4, sketch the given rightward moving wave made on a rope after it has reflected off of a fixed end. Here we have a little wave pulse coming in. It's reflecting off of a fixed end. Off of a fixed end, it is of course going to reflect back, but it is also going to invert its orientation. So where it was coming from the left going to the right, it is now going to be coming from the right going to the left, and instead of it being on the top of that rope, you could say now it's on the bottom. It has reflected, changed directions, and inverted. So here, change directions, and it inverts. What about when we have a free end? If we have a free end, we're still going to get that reflection. We're still going to change direction, but there is not going to be any inversion. So let's draw our wave. Instead of coming in to that ring, now it's going out. Does not flip over onto that bottom side. And this is for a loose end, no inversion. Whether it's a fixed end or a loose end, it's gonna change directions. If it was moving to the right, it's gonna be moving to the left. If it's moving to the left, it's gonna be moving to the right. But only the fixed end is gonna invert its orientation, like you see here. What type of wave is sound? Well, sound is a longitudinal wave. We often represent sound as a transverse wave, but sound actually is a longitudinal wave. That is really a compression wave. It looks a bit like, if we use a slinky as an example, where the slinky is not very compressed, then an area where it is really compressed, then an area where it's not very compressed, and this cycle continues. When you have a transverse wave, you have crests and troughs. Longitudinal waves have compressions like so, where there's a high density, and rarefactions, like so, where there's a much lower density. Another important piece of longitudinal waves is that the medium, what the wave is actually made out of, or really what it's traveling through, would be a better way to phrase it, the medium is moving back and forth in the same direction that the wave is traveling. So since the wave is going, let's say, from left to right here, the medium in a longitudinal wave is going to oscillate parallel. So to the right, to the left. The spring itself isn't moving to the right. It just looks like it is. The wave is moving to the right. The spring itself is staying mostly in place. It's just oscillating about a point to the right, to the left. When a wave made in a slinky on the ground travels from you to your friend holding the other end, the particles in the slinky, we have a couple of different options. So the wave is made in the slinky on the ground, travels from you to your friend holding the other end. The particles in the slinky, well, they definitely move. We can get rid of do not move. Move parallel to the motion of the wave, move perpendicular to the motion of the wave, or travel with the slinky wave. It's not going to be travel with the slinky wave. That means if we sent a bunch of waves, eventually the person sending the waves wouldn't have any slinky left in their hand, because all the slinky would have traveled with the wave. We know that's not true. Waves don't carry matter, they just carry energy. Now we just have to decide, is it going to be parallel? Is it going to be perpendicular? Well, this really depends on the type of wave we're making in the slinky. Since we made these waves in class, I'm going to presume that we're talking about a transverse wave. In a transverse wave, we get a pattern that looks something like this. We can draw on our dotted line for the undisturbed medium. We have crests and troughs. In a transverse wave, and this is a transverse wave right here, the medium, and I'll do it in the same color coding we did before, the medium is going to oscillate perpendicular to the direction the wave is moving. So again, if our wave is moving to the right for a transverse wave, the medium, whatever the wave is traveling through, is oscillating up and down, perpendicular to the direction the wave moves. For a longitudinal wave, the one we have right over here, the medium is oscillating parallel to the direction the wave is moving. If the wave is moving to the right, medium is moving left and right. For a transverse wave, if the wave is traveling to the right, the medium is oscillating up and down, perpendicular to the direction of that wave motion. So here, assuming we are making a transverse wave, this would be perpendicular for transverse, and it would be parallel for longitudinal. If you struggle to remember this, how do you remember transverse is perpendicular and longitudinal is parallel? A trick I like to use is if we look at that T in transverse, the capital T there, those are perpendicular lines. In fact, if you flip that T upside down, you get the symbol for perpendicular lines, just an upside down T. Remember that T in transverse, you can use that as a symbol. These are perpendicular lines, matches with our perpendicular symbol. Transverse waves, the medium oscillates perpendicular to the motion of the waves. For longitudinal, is there a little trick there? Well, there actually is. We have two L's in longitudinal, one at the very beginning, one at the very end. Those two L's, they look kind of like parallel lines. Longitudinal waves, the medium oscillates parallel to the direction of wave motion. Just two little tricks you can use to help yourself remember. Number 8, when a sound wave is made that travels from left to right, the air molecules, we know the air molecules are moving. We know they do not travel with the sound waves. The air molecules are not moving from my mouth to your ear. They are just oscillating, moving back and forth, ever so slightly. Since we know sound is a longitudinal wave, and longitudinal waves move parallel, the medium moves parallel to the direction of wave motion, and the wave is traveling from left to right, those particles, those air particles, are going to be moving left to right as well. All right, number 9. Doppler effect causes an apparent shift in the frequency we hear when a source of sound moves away or toward us. Explain how the apparent frequency changes. Use a diagram to support your explanation. Well, the apparent frequency is going to change depending on if they're moving towards or away from us. If they are moving towards us, that apparent frequency is going to increase. If they are moving away from us, it is going to decrease. What exactly does this look like? Well, let's draw out instead of drawing a person, let's draw maybe a vehicle. Let's say we have an ambulance, and it's got its siren blaring. So this is an ambulance. Maybe we'll make a little plus sign for the hospital. We'll give them a little alarm right here. Let's say that's their siren, right? And that siren is producing sound, right? We hear it as they go past us. If they are moving with some velocity to the right, the sound waves that are emitted right here, they're going to stack up in the direction the object is moving. Because in the time that they're emitting sound waves, they have moved to the right. So that next crest is going to be a little bit closer to the crest that they just emitted a moment ago, because they've moved more to the right in that time. So if you are standing over here in the direction that the vehicle is moving towards, you are going to hear a higher frequency just because the distance from crest to crest, the wavelength is shorter. So you interpret that as, well, wavelength decreases, frequency increases. You hear that higher pitch, that higher frequency. If you're standing on the other side, away from the vehicle, it's moving away from you, that frequency you're going to hear is going to be lower. Because those wave fronts, those crests right here, they are further and further apart than they usually would be if the object emitting the sound was stationary. Because of that distance, that increase in wavelength, you interpret that as a decrease in frequency. And you hear a lower pitch when they're moving away from you. Does sound travel faster through hot air or cool air? It travels faster through hot air. You can remember this in that, well, as temperature increases, the particles in the air are moving faster, so it's faster for them to exchange that energy, for the energy to travel through them when it's hot, when they're moving faster. How does the equation for the speed of sound support your answer to the previous question mathematically? Well, if we look at our equation for the speed of sound, which is right up here, and let's go ahead and highlight that. This is our speed of sound equation with regards to temperature. We have that same equation. So speed of sound in air, 331.5 plus 0.6 T for temperature. What this is really saying is that as temperature increases, well, this factor right here, this term, is going to get bigger and bigger. Meaning, since that's added to our 331.5, that speed of sound is going to increase. We can use this equation to calculate the speed of sound when it is 19 degrees Celsius outside. Write out the speed of sound is equal to 331, and we're just not writing in our units to save some space, plus 0.6 times, we're multiplying by 19 degrees Celsius. So, if we go ahead and say 0.6 times 19, this gets us 11.4. We're adding that to our 331.5, which is going to give us a speed of sound in the air at 19 degrees Celsius of 342.9. Don't forget your units, meters per second. If you look up at this equation and all these units are confusing you, just simply don't write them. Where we have meters per second doesn't mean you're plugging in a distance, you're plugging in a time. These are just units attached to this velocity. Meters per second per degree Celsius, these are just units attached to this constant. You're not plugging anything in there. The only place you're plugging things in this equation is for T, right here, the temperature. Alright, on to our third page. Number 13, you're standing on a cliff facing a distant mountain. You yell echo and start your stopwatch. You measure 2.2 seconds until you hear the echo of your voice. It is 19 degrees Celsius outside. How far away in meters is the mountain? Okay, so this is an echo problem, as you can tell. We are going to draw a picture. I love to draw a little picture for an echo problem. Let's say we have our mountain right here, and we're standing over here. We yell echo. Sound is going to travel all the way to the mountain, and it's going to travel all the way back to us so that we hear our echo. It takes a total time 2.2 seconds for it to travel there and back. We know the temperature. Because we know the temperature, we can calculate how fast sound is. We're just going to use our equation right up here like we did earlier and say that that speed of sound is 331.5 plus 0.6 times the temperature. If we plug in that temperature of 19 degrees, like we did right up here, we're going to get this same velocity. So the speed of sound is 342.9 meters per second. Now we have a speed of sound, we have a time. We are trying to find out how far away is the mountain. Well, that mountain is a distance away. We could abbreviate that distance away as d, but this distance, we can't use our total time. We have an equation. We could say delta x, that distance, that displacement, is equal to velocity times time. We have a velocity, we have time. Are we good to just plug everything in? Not quite. Because while that velocity is absolutely correct, that's how fast the sound is traveling through the air, it travels more than a distance of d in 2.2 seconds. That total time is the time it takes to go there and back. What we really want to plug in, since we're only looking for how far away is the mountain from where we are standing, we don't want the time it takes to go there and back, we just want the time it takes to get there. The time it takes to get there is just going to be half of that total time, since it's traveling half that distance. Plug in 1.1 seconds. Now we're all set. We can go ahead and multiply these. If we do that, we're going to get our answer 377.19 meters away. If alternatively you did not change this time, you plugged in 2.2 and you get a bigger number over here, that's okay. Just take your bigger answer, divide that in half. That distance that you got would be the distance there and back. If you cut that distance in half, now you get just the distance there. Okay. Explain how standing waves can be made in a slinky or a spring. Well, standing waves, and we're just going to talk through this one. Standing waves are made when you find a certain frequency that matches with the spring or slinky, what it would naturally resonate at, and that resonance increases the amplitude of the waves. What you get is a lot of constructive and destructive interference. Constructive interference, where those crests are meeting other crests, the amplitude becomes really, really large. Same thing where troughs meet troughs, the amplitude becomes really, really large. At your nodes, those points of no motion along the standing wave, you're getting destructive interference. A crest is meeting a trough, and they're canceling each other out. So the spring or the slinky stands still. Number 15. Standing wave is produced in a rope, which is fixed at each end. At each end of the rope, there is a blank. Well, if we have, say, a rope, and let's say we make a standing wave pattern, this would be a 3-loop standing wave pattern. Since it is made on a rope, there is always going to be a node at each end of that rope. The nodes are those points of no motion. At the end, there's something holding that rope in place. It is not moving. Draw our first 5 standing wave patterns for a rope that is fixed at both ends and 5 meters long. Next to the standing wave, write the wavelength. All right, let's go ahead and do it. So, first standing wave pattern, I'm going to do 1/2 like this. We could even draw in our second part of it, like so. 2 loops, the second pattern. Three loops for our third pattern. Ideally, my loops would be the same size, but I am working with what I can do. And we'll have 5 loops for our 5th pattern. Okay, now we know our length. From one end to the other end, it is 5 meters long. 5 meters. What we could do is we could highlight one full wavelength. Full wavelength is a full crest and a full trough. Another way to think about it is a full wavelength is 2 loops, since every loop is half of a wavelength. These are all a full wavelength. We can see as we make more and more loops, that wavelength is decreasing. Now, we want to solve for our wavelength. How exactly are we going to do that? Well, one way you could set this up is to say, just like we did in our not our standing wave lab, but in our speed of sound lab, we said for our length, we have some fraction of wavelength. So our length is 5 meters. On this first pattern, we just have one loop. That is half of a wavelength. For our second pattern, we have 1 wavelength. For our third pattern, this is going to be 1.5 wavelengths, or 3/2 a wavelength. For our fourth pattern, this is 2 wavelengths, and for our fifth pattern, this is going to be 2.5 wavelengths, or 5/2. You could rearrange these equations, plug in 5 for our length, and you'd find if you just cancel our constant that we have, right out here, 1/2, 1, 3/2, just cancel it out by multiplying both sides, just like you're solving an algebra problem, right? We're solving for wavelength. How do we cancel multiplying by 1/2? Well, let's multiply by 2. If we do that, we'll cancel out that 1/2. We don't have to do anything to our second pattern. Our third pattern, multiply both sides by the reciprocal, 2/3. We'll cancel our 3/2. On this one, 2, how do we cancel that 2? Well, we could divide by 2. We could also multiply by 1/2. And to cancel our 5/2, multiply it by 2/5. This works. You'd just plug in that 5 meters for L, and you'd get your wavelength for each of them. Let's do this in pink. Wavelength for the first one, well, 2 times 5 would give us 10 meters. 1 times 5, our wavelength would be 5 meters. For our third pattern, 5 times 2 divided by 3 would be 3.33 meters. 1/2 of 5 would give us 2.5. And our last one, 5 times 2 divided by 5 would give us 2 meters. Now, in my class, I did teach another equation to solve for the wavelength. That is that the wavelength is 2 times the length of the string, the rope, the tube, whatever the object is, divided by n, where n is your number of loops. Sometimes this is a whole number, sometimes it is not when you're dealing with standing waves in pipes, but this equation will also always work for calculating the wavelength. The trouble with it is that people get confused and think that n does not mean number of loops, that it means something else. You can use either way. Either method is going to get you the correct answer. It's just up to you to decide which method works better for you. You can use the length and figure out how many wavelengths that is, like we did on the left, or you can use the wavelength is 2 times the length over the number of loops. You'll find you get the same answer either way. Let's move on to page 4. The third pattern is made in the 5-meter long rope from the previous problem by shaking the rope up and down 25 times in 12 seconds. Calculate the frequency for this standing wave. Well, frequency, lucky for us, we know this equation. It's not given to us, but we know frequency is the number of cycles per second. So let's plug in our number of cycles, 25 cycles, up and down 25 times, and let's plug in our time, 12 seconds. 25 over 12 is going to give us 2.083. Now what's our unit there? We have seconds in our denominator. Our unit is hertz, inverse seconds, 1 over seconds, all the same thing. Hertz is what we use for frequency. Using the wavelength you found, calculate the velocity of the wave in this rope. Well, we did not find a wavelength. Actually, we didn't find a wavelength. They're talking about in number 16. For our 3-loop pattern, we found a wavelength of 3.33. Let's bring it on down here just so we remember, 3.33 meters. We have our frequency. Velocity, we have our equation, the wave speed equation. Velocity is frequency times wavelength. How many waves you're making in a second times how long those waves are. Plug in our frequency, plug in our wavelength, we'll get our answer. 2.083 times 3.33. And we get our answer, the velocity, 6.94 meters per second. What would be the velocity of the 4-loop standing wave? This one, tricky question. The velocity is set by the medium. You might think, oh, well, our wavelength got smaller, right? It went from 3.33 to 2.5. Doesn't that mean that the speed is going to get smaller, right? If we look at our equation, our wavelength gets smaller. Shouldn't our velocity get smaller? Not here, because even though our wavelength gets smaller, our frequency is going to go up. If you think about the Standing Wave Lab, to make more loops, you had to move your wrist up and down more times in a single second. You had to increase your frequency. So as that wavelength is decreasing, your frequency is increasing. Those increases and decreases are proportional to each other. So that if, say, the wavelength is cut in half, the frequency is going to double, so you end up with the same velocity. That velocity will still be 6.94 meters per second because velocity is set by the medium. So no matter how many loops you make on this same spring, it is going to travel at the same speed.
All right, on to page number 5. 18. A wave is made in a spring and the motion of one coil of the spring versus time is shown below. You collected data for 8 seconds.
All right, so how many waves did you make in 8 seconds? Well, how do we determine that? We have to look at how long a wave is. A wave is just measured from crest to crest or trough to trough. Pick either, and we're going to say, we're going from crest to crest, that's 1. Or trough to trough, that's 2. So you get 3, 4, 5, 6, 7, 8, 9, 10, 11. And you might say, Mr. Rosauer, there's more than just that, right? If we look at those endings, we're ending the wave right here and right here. What about the parts that are outside of there? Isn't there a little bit of wave there? What do we do with that? There absolutely is. But we're just going to estimate that it is 11 waves. Part B, calculate the frequency of the waves being made. Well, frequency. Again, our handy-dandy equation. Cycles per second, an equation you absolutely need to have memorized. We make 11 waves in 8 seconds. So if we plug this into our calculator, we'll find this is going to give us 1.44 hertz for our frequency. That's a really, really low frequency. Draw the first 3 standing sound waves that can be created in a closed open tube below. You should draw the sound waves as transverse displacement waves instead of longitudinal sound waves. Excellent. So, we have our closed tube. We know the closed end. You are always going to have a node on that closed end. These are all nodes where the air particles are not moving. Then, we get our half loop right here. Half loop right here. Over here we have our antinode, that maximum displacement of the air particles. Our second pattern, we're going to have a full loop and half a loop. It's going to look something like this. Let's close that full loop. I totally missed my dot. Let's try that again. Much better. Here we have another node right here. Right, that dot. Where the lines intersect. That is a node. And our antinode right here. We do have another antinode inside the pipe. And our third pattern, we are going to have 2 nodes within the pipe, not counting the one that's at our closed end. Alright, we have a node, here is an antinode, here is an antinode, and here is an antinode. We've labeled the nodes and antinodes. If the length of the tube is 3 meters, write the wavelength of each sound wave in the space to the right of each tube. Well, again, for part B, we can calculate this in one of 2 ways. We can say, and I'll split this down the middle, we can say, use the length of the tube, find out a fraction of how many wavelengths there are. So for the first one, we have the length, we know, is 3. In that 3-meter tube, and again, our tube measured from one side to the other is 3 meters. That's where we're getting our length. We have half of a loop, so a quarter of a wavelength fits in this pipe. What about when we have our second pattern? The length is still 3 meters, but now we have 3 quarters, or rather, we have 1 full loop and a half loop, where we fit 3 quarters of a wavelength. The full wavelength would be 2 full loops. We're not quite there. We're 3 quarters of the way there. And our final pattern, we have a full loop, a second full loop, and a half loop. So this would be 1 1/4 wavelengths, or 5/4 a wavelength. You can then just solve this for the wavelength. Get rid of this fraction by, for instance, multiplying by 4 on each side, multiply by 4/3 on each side, multiply by 4/5 on each side, to undo, to cancel what we have next to our wavelength. If you wanted to use that other equation we mentioned earlier, wavelength is 2 the length divided by number of loops. Again, this n is the number of loops. You can absolutely do that. You're going to get the same answer either way. What would that look like? Well, you would say, alright, so where were we? We were just talking about number 19, using our other equation as an option, in case you wanted to, where we have wavelength is equal to 2L over N. You get the same exact answer as using the other option. If the temperature in the room where these standing waves were made is 22 degrees Celsius, calculate the speed of the sound wave in the room. Okay, for this, we're going to use our speed of sound equation that uses temperature. So let's bring that on down. Speed of sound is equal to 331.5 plus 0.6 T. Now this T is the temperature in degrees Celsius. I've removed our units here because oftentimes these units, they can really confuse students. All they're doing is they are there because on the left-hand side, we have the speed of sound. Speed of sound is measured in meters per second, so we need our units on our right-hand side to also match our units on our left. On the left, we have meters per second. On the right, we must also have meters per second. So this meters per second and this meters per second per degrees Celsius are just there to give us those proper units. They're not variables that you are plugging things into. They are just units. What we are plugging into is that temperature. So we will plug in 22 degrees Celsius to our temperature. We can solve this. 0.6 times 22. Let's go ahead and plug that into a calculator. We get 13.2. We're going to add our 331.5 to get that speed of sound. 331.5 plus 13.2 is going to give us the velocity of sound, 344.7. And of course, we tack our units on there, meters per second. Using parts B and C, calculate the frequency of the first 3 sound waves in the space below. I never wrote down the actual wavelengths. Let's go ahead and do that. So the first one, the wavelength. If our tube is 3 meters long, 4 times 3, just using our equation on the left there, this would be 12 meters. 4 times 3 divided by 3, our wavelength would be 4 meters. And 4 times 3 divided by 5, our wavelength would be 2.4 meters. Alright. For the first pattern, second pattern, and third pattern, calculate those frequencies. Well, we are just going to be using velocity as frequency times wavelength. So, for our first pattern, we know the velocity. It is going to be our 344.7. That's going to be consistent for each pattern, because no matter the pattern, the medium sets the wave speed. So because they're all traveling through the same air at the same temperature, they're all going to be traveling the same speed, no matter their frequency or wavelength. So 344.7 is equal to frequency that we're solving for times our wavelength. Wavelength for the first pattern is 12. If we go ahead and solve this, we are going to get frequency 28.73 hertz. For our next one, same speed. Our wavelength is now 4. That's going to get us a frequency of 86.18 hertz. And our last pattern, that third pattern, we are going to plug in, again, that same wave speed. And our wavelength is 2.4 meters. Divide both sides by 2.4. And we find our frequency is 143.63 hertz.